Many people find the logical operation of implication to be very confusing, and there are a lot of reasons for that. One is that the statement P implies Q is often given as a true statement. You don't have P, you don't have Q, but you know that P implies Q. P and Q would be some kind of specific statement. And in doing reasoning, you're given that P implies Q, and you're given that Q implies R, say, and then you need to know whether there's some further implication that you can draw. But you're given this implication. On the other hand, implication itself has this truth table, which is, I've written it, by the way, as a truth table, not with ones and zeros, to emphasize where people get confused about it, because what you have is two propositions, P and Q, and the logical operation P implies Q, and this is what we take these things to mean. And a lot of people find that that doesn't make any sense. So what we want to do right now is demonstrate to a certain extent why that makes sense, and which also illustrates an important strategy for understanding other logical propositions. And then we're going to prove a logical statement typical of the kind of stuff that's in section 3.5 of our book. But this is the most important one, and then that'll be this. When we go on to talk about proofs, which is the next topic, then we're going to start using this stuff to prove interesting things. So first we got to worry about this thing, P implies Q. And one way that you know that you understand any kind of definition is if you understand it and its negation. So you might remember working with intervals in the real number line, and a closed interval includes its endpoints. What's the negation? Well, one of the endpoints isn't missing, and so that tells you kind of both sides how to look at this. So one of the best ways to understand implication is to understand its negation, but in order to do that, we have to do some work with the truth tables involving P, Q, and P implies Q. There's a lot of practice that went into this. I didn't just sit down here and say, oh yeah, I'm going to do this. I've been working on this. I've been working on this for years and years and years to help you understand it. And so let's get right on into it. So here's the implication truth table. I'm going to start over, and that will very quickly become clear. Something to bear in mind about truth tables is that in this case, with two propositions P and Q, then the truth table only has 4 rows, and so that's something that's tractable on an ordinary piece of paper. If you have something that has many, many, many different statements involved in it, which would be typical in complicated mathematical statements or complicated statements in computer science, the kind that we're going to bump into later on in this course when we're doing graph theory, then the truth table becomes unwieldy because its growth is exponential. Every time you add a proposition, you double the number of rows in the truth table, and that very quickly gets out of hand. So a 10 proposition statement has a truth table with 1,024 rows. You can't do it by hand. You might be able to do it by machine, but if you get much bigger than that even, then you can't even do it by machine within any practical time. Okay. So let's go back to this truth table, which has 4 rows, which is tractable. And so I'm filling in the typical values of P and the typical values of Q and the value of the implication. I'm switching back to zeros and ones so that it becomes a little bit more tractable. And now we need to start fooling around with things. And this is something that you might be able to do, you might not be able to do, but one of the important things, which I just said, is that if you want to know about something, you also need to know about its negation. So what I'm going to do is add to this truth table a column for the negation of P and a column for the negation of Q. And then we're going to look at those and see what we can discover. So I am writing in the negations of P and Q. So P is 1100, its negation is 0011. That's pretty elementary. And there's something that you might be able to see straight away, which is you can play with this and make up things. So you're going to start doing ands and ors and nots and so forth and so on. Don't use implication in trying to understand implication. Use ands and ors and so forth and so on. And that goes with anything. Don't use the thing itself to try to explain the thing itself. I guess that could be called circular reasoning. And so I admit I fooled around with this a little bit before I decided to settle on looking at the following logical operation. I'm going to take P. P is a proposition. I know. Here's its values, all the possible values of P. And I'm going to take the negation of Q, all the possible values of the negation of Q. And let's look at their and. Now, and is true exactly when both of them are true. So you kind of have to have a big span here. I'm looking down at these two columns. And so let's see. 1 and 0 is 0. 1 and 1 is 1. 0 and 0 is 0. 0 and 1 is 0. So there is another logical operation. So if we know the truth value of P and Q, we know the truth value of P and the negation of Q. Now take a look at this, because it's this is where the important things happen. If I look at the column for P implies Q and the column that we just made for P and not Q, well, I've got 1, 0, 0, 1. I got 1, 0, I got 0, 1. So this pink column is the negation of implication. So it did take me a couple of tries to find that. I mean, when I first did it, I mean, I've been doing this for years. So it took a couple of tries to find that. And so what I'm going to do is now switch over to the negation of that pink column. So I'm going to negate P and not Q. And that's a pretty simple thing. If one of them is 0, its negation is 1, and vice versa. And what we see here is that the negation of P and not Q is the same thing as P and Q. Okay, that's a big deal. So let me kind of highlight it. P implies Q is equivalent to the negation of P and not Q. Big deal. Okay. Well, being equivalent to the negation of something is kind of mean. What is going on? So what I'm going to do now is negate P implies Q. This is the only way to reliably negate implication. People try to make up something that is a not implied kind of thing. This is the only way that's known to do this. And there's so few elements to this reasoning here that you could combinatorially check all of them. And this is the only way. This is the only way to negate implication. And that's going to tell us exactly what's going on. So first we're going to make a simple step, and then we're going to apply De Morgan's laws. So the simple step is that the negation of P implies Q is equivalent with P and not Q. So what I had here in green is a logical equivalence, and I've negated both sides. Now the negation of a negation is going back to the original, and so this is now P and not Q. So this is what P does not imply Q means. It means that P, wow, This is kind of mind-blowing. P does not imply Q. I'm writing this in words. What that means is that P is true and Q isn't. Well, that's what not implies means. P doesn't imply Q. If you can find a situation where P is true and Q isn't, then P does not imply Q. So we get to understanding of implication through the negation. And so, I didn't finish writing it out, means P is true and Q isn't. That doesn't sound like implication to me at all. So we'll mark that with some big stars and put it in a box and wrap it up with a ribbon. And so this is why implication has the truth table that it has.